Exercise 9.4, factoring algebraic expressions. Factoring is doing the reverse of multiplication. So the distributive property we talked about the past couple of days, foiling that we talked about the past couple of days, we're now going to undo that process by the method of factoring. What we talked about with foiling was taking two binomials, multiplying them together to get to this trinomial. Now today we're going to begin with a trinomial, and we're going to rewrite it into the two binomial factors that when multiplied together equal the given trinomial. When you are factoring, the first thing you should always look for, no matter what type of factoring problem it is, how simple, how complex, doesn't matter, always look for a greatest common factor. Greatest common factor is take that out, or factor that out at the beginning before you do anything else. So in this first expression, ax plus ay plus az, in common to all three of these terms, is a factor of a. If I take an a out of that first term, I'm left with x. Take an a out of the second term, I'm left with y. Take an a out of the third term, I'm left with z. And there is factored form. Once it's factored, if you distribute back through, you better get what you started with. In this case, ax plus ay plus z when I multiply that back through. Second one, in common to everything here, we have an a and a b. So I can take that and factor it out. Take an a and a b out of that first term, we're left with c. Take an a and a b out of the second term, we're left with d. Take an a and a b out of the third term, we are left with f. Again, if we were going to distribute that back through, we would get back to our original expression. Third one, a to the fourth plus a cubed plus a squared. They all have an a in common. What's the most number of a's we can take out? We're limited by that third term, which only has two of them. Take two of those a's out of those four, we're left with two. Take two of the a's out of those three, we're left with one. Take both of those a's away, and we are left with no a's, but we need to leave a 1 there to hold that place value position so that when I distribute this back through, I get a to the fourth plus a cubed plus a squared. If you don't put that 1 in there, you're not going to hold that place value position. Fourth one, what can we take out of here? Well, we can take both a 3 and an x out. Take a 3 and an x out of that first term. We need a 1 to hold that place value position, or term position, I should say. Take a 3x out of the second one, left with x. Take a 3x out of the third one, we're left with x squared. We cannot go any farther in factoring. Factoring a trinomial into two binomials, again, is FOIL in reverse. We're going to start with the trinomial now, and we want to come up with the two binomials that when multiplied equal the trinomial. So we see a trinomial, three terms, automatically think of factoring it into two binomials. First term has to multiply to be the first term, so x times x has to equal x squared. Now our second combination, when the lead coefficient is 1, we're looking for numbers that multiply to be 9 and add to be -6. So we're looking for factors of 9 that add up to 6. Those factors are positive 3 and positive 3. We can simplify this and write it then as x plus 3, the quantity squared, since those are the same exact two factors. Second one, x squared minus 6x plus 9. See a trinomial, automatically think of two binomials. Again, going to be x and x. Now we're looking for numbers that multiply to be 9 and add to be -6. Factors that multiply to be 9 and add to be -6 are -3 and -3. So we can write that as x minus 3, quantity squared. Third one, two binomials. What times what equals y squared? Y and y. What numbers multiply to be -4 and add to be positive 3? Anytime the numbers have to multiply to be a negative, remember we have to have one positive and one negative. So we're looking for a positive and negative factor of 4 that add up to be 3. That's positive 4 and -1. The last trinomial here, has to be a and a. Again, we're multiplying to be a negative, so I know we have to have opposite signs. Factors of 6 that add up to -5 are -6 and +1. The difference of two squares. Anytime we have two perfect squares that are combined only by a subtraction, notice this is a difference of two squares, so it must be a subtraction. It always factors into square root of the first thing, minus square root of the second thing, square root of the first thing, plus square root of the second thing. So in this case, x squared plus y squared. Square root of x squared is x. Square root of y squared is y. So we have x minus y times x plus y. N squared minus 16. Square root of n squared is n. Square root of 16 is 4. So I have n minus 4 times n plus 4. 4a squared minus 9b squared. Square root of 4 is 2. Square root of a squared is a. Square root of 9 is 3. Square root of b squared is b. So I have 2a minus 3b times 2a plus 3b. Fourth one, x to the fourth minus 25. Square root of x to the fourth is x squared. Square root of 25 is 5. So I have x squared minus 5 times x squared plus 5.